All right, hello class. Welcome to the new unit number 7. This is the second and last unit that has to deal with trigonometry. So you're going to notice we're going to build off last unit. We're going to go over some things that were similar to last year, and then we're also going to dive into some new concepts as well. So today we're going over lesson number 1. That is 7.1, exploring equivalent trig functions. So basically that means we're going to come up with two expressions for two different trig functions, right? So they're going to look like two different equations, but they represent the same graph. So they're equivalent, right? So they might look different, but when you put it down on paper, it's actually the same graph. So to get thinking here, it says write an equation to represent the following sinusoidal function. So the one that was in light blue, so the one that's blank on your page. So if I asked you to do this last unit, you would highlight a cycle of sine or cos that you could see, and then you would use its characteristics to come up with an equation. So the first thing that we can do here is, I'm just going to go over at the side here some of the characteristics I notice. So I notice that my equation of the equation of axis is y equals 0. Okay, so that means c equals 0. Right. What else am I noticing? I notice that if I were to highlight, so for example here, this blue graph starts at the EOA, and then it looks like a reflected sine, right? So that looks like a reflected sine, and so it looks like the period goes from 0 to 2 pi. So the period is 2 pi, so therefore k equals 1. Right, because 2 pi divided by 2 pi is 1. I also noticed that the amplitude is 1 unit. Okay. So it looks like if amplitude is 1, k is 1, c is 0, it looks like the only thing that might be affected here is the d value, depending on what I highlight. So for example, if we were to look at the blue graph here, so that's sine, I would notice that that is the sine function with a d value of 0 because it starts at 0. However, it's reflected, so a would be negative. So an equation for this graph could be f at theta equals negative sine theta. Okay, so amplitude 1, k value 1, and then d and c are also 0. Someone else could have looked at this graph and then highlighted the first cos graph that they saw. So that would be what I have here in green. So if we did the cos graph, it would have all those same characteristics. Because we opened one that was opening up, so it started out as max, that means that our a value is positive, so it's going to be positive 1. And what's going to be different here is its d value. So its d value starts at negative pi over 2. So that means the equation for the green graph would be cos theta plus pi over 2, because remember, this indicates that it was negative on the outside. Someone else looking at this may have highlighted a different sine cycle, so they might have highlighted the one that I have here in red. Okay. In that case, the amplitude, of course, is still 1, but because we go from our EOA to our max, that means that a is positive 1. So, and then what's interesting here is that the d value for this sine cycle is negative pi. Okay, so for the red, the d is negative pi. Okay. For the green, the d was negative pi over 2. Okay, so if I were to plug that into an equation, then the equation for the red graph would be f at theta equals positive 1 sine theta plus pi, because the d was negative pi. So all of these answers are correct. So if someone put this on a test, that's correct. Someone put this, that's correct. And if you notice, we can keep going and going because these functions keep repeating themselves over and over and over again. So you can highlight one that starts over here. You can highlight a negative cos function, right? A cos that's been reflected. So basically, there's an infinite number of possibilities for the equations that you can make. So we would call these three equations equivalent trig functions. Okay. So because of their periodic nature, there are many equivalent trig expressions. So two expressions are considered equivalent if, when you graph them, their graphs coincide. So coincide means that they overlap, okay? Producing only one visible graph over the entire domain. All right, so there's a bunch of different tricks and ways that we can find this. So we're going to go over a lot of them today. There's 5 of them, so there is a lot to cover. But rest assured that out of the 5 of them, you're always given all the formulas for the first 4. So you can always have that at the side. It's at the side when you're working. Okay. All right. So the first one pertains to using the period of a function. All right. So we notice that two expressions are going to be equivalent if they are integer multiples of the period from each other. So that means, I'm going to kind of highlight here. Okay, so that means if I were to highlight sine here, right, this is one sine cycle. Okay, so this is sine theta. I would actually, if I highlighted a second sine function that would start here, okay, notice that this starting point would be at 2 pi. If I were to highlight another sine cycle, okay, it would be here starting at negative 2 pi. And if you notice, it's just going to keep repeating this for every amount of the period. So I can go back 2 pi, back another 2 pi. I can go forward 2 pi, forward another 2 pi. So I'm noticing that because sine's period is 2 pi, that means an equivalent expression for sine theta. So an equivalent expression for this graph would be, if this is sine theta, then equivalent graph would be sine theta plus, or you could say, or minus, plus 2 pi n, okay, where n is an element of integers. So basically that's saying, so for example, if I put n equals 1, so I put n as 1, so that would be theta plus 2 pi. Yep, that would make sense. It starts right here at 2 pi. If I were to plug in n equals 2, that would be theta plus 4 pi. And that would be the same graph again because the graph repeats every 2 pi. So any integer that I plug in here, multiply it by 2 pi, and then add or subtract it on, so it can be positive or negative. All right, so if it's, so in this case here, if you plug in a negative value, this would be negative, and then that means you would be going to the right. And then if you plug in a positive value, that will leave this amount as positive, so that means you would go to the left. All right, the same idea works for cos. Because cos has a period of 2 pi, so let's start with cos's main graph here. So cos repeats itself every 2 pi as well, right? So its second cycle could be here. Right? And it starts at negative 2 pi. Its new cycle would also start at 2 pi, right, if it were to continue as well. All right, so same holds true there. So an equivalent expression for cos theta is cos theta plus 2 pi n, where n is an element of integers. Okay, so basically it says you can keep adding or subtracting multiples of the period. All right, tan theta, same concept, but keep in mind that tan's period is pi. So that means it can only be, you can only add integer multiples of pi. So tan theta equals tan theta plus pi times n, where n is an element of integers. So again, highlighting here, So for example, if you highlighted that as your start for tan, try to do this. There we go, looks better. If we add another pi to this, so right, if it's starting there, another pi to it, it would go to this. If we subtracted pi from this, it would become this. Okay, so because all you'd be saying is that you were moving this blue graph pi to the left, right? And that would be right. It would fall on top of itself. And if you did pi and you shifted it to the right, again, it would overlap itself. So if I say find an equivalent expression using these formulas, so using equivalency according to the period of a function, and I say find an equivalent expression of sine 7 pi over 8. So obviously in this case, the theta is what's given, so 7 pi over 8. So I know my expression is that sine theta equals sine theta plus 2 pi m. So in this case, if I just say find an expression, you get to pick what your n value is, okay? And that's, again, unlimited. So choose any integer. So for example, for this one, I decide to choose n equals 2. Okay, so now I'm going to plug in 2, and wherever I see theta, I'm going to plug 7 pi over 8. Right? So basically, I'm rewriting this as this. Okay, so sine 7 pi over 8, according to the formula, is equal to sine of 7 pi over 8 plus 2 pi times 2. Right? That's the integer I chose. So that is sine 7 pi over 8 plus 4 pi. In order to combine this, we want one simplified expression. We have to find a common denominator of 8. So multiply top and bottom here by 8. And that leaves us with sine 7 pi over 8 plus 32 pi over 8. And that becomes sine 39 pi over 8. So we just found an equivalent expression. Okay, so we found out that if I were to plot sine 7 pi over 8, it would be the same thing as if I graphed sine 39 pi over 8. Okay, so these two graphs would coincide. And that's how we use the period equations in order to come up with an equivalent expression. All right, let's move on to part 2. So part 2 deals with classifying a function as even or odd. Okay, and what I mean by that, even or odd symmetry. So add that word in. This is not even or odd degree. We don't deal with degrees with sine and cosine trig functions. Okay, that's only for polynomial functions. So even or odd symmetry. So for this one, I want us to kind of refresh our memories a little bit. So remember even functions. How could we tell something was even based on a graph? So if you remember, it meant that it was symmetrical about the y-axis. So that meant if you reflected across the y-axis, it should overlap itself. Okay. If it was odd function, graphically, it should have had rotational symmetry 180 degrees about the origin. Okay. So remember, you put a pin at 0, 0, rotate it 180 degrees, and it should overlap itself. All right, to come up with these equations, okay, we are going to have to remember the formulas that we use to prove whether something was even or odd symmetry algebraically. So this is a good review of Unit 1. So let's remember, if it was even symmetry, when we subbed in negative x and simplified, if it was even, then you should have gotten f of x back. Okay, so this is important. So f at negative x should equal f of x. If it was odd symmetry, when we subbed in negative x, we should have gotten negative f of x back. So the original function multiplied by negative 1. Okay, so very important here. We're going to apply these rules to the sine, cosine, tan functions. So looking visually at sine, I can see that it has rotational symmetry about the origin. If I were to put a pin here and rotate this 180 degrees, it would overlap itself here. So sine has odd symmetry. So knowing that, that means I'm going to rewrite it using this formula up here. Okay, so odd symmetry means I'm going to write that sine negative theta, so same thing here, is equal to, and then I'm going to write negative sine theta. And that is one new equivalency formula. All right, if I look at cosine, I can see that cos would overlap itself if I reflected it across the y-axis. So that means it has even symmetry. So that means it's going to follow this formula up here. So when I do cos negative theta, if it's even, it should just produce cos positive theta back. Okay? So cos negative of an angle equals cos of its positive angle. Tan. So looking at tan, I can see that if I were to put a pin right here at 0, 0 and rotate it 180 degrees, it would overlap itself because this little part here would eventually cover here, and the asymptotes would cover the asymptotes again. So tan is like sine, and it has odd symmetry. So that means it's going to follow this rule up here. So it's going to be tan negative theta equals negative tan theta. Okay, so -1 times just tan theta on its own. All right, so now we're going to apply these three new formulas to find equivalent expressions and examples. Okay, so here we have find an equivalent expression of cos negative 5 pi over 8. Okay, so I immediately go up to the cos equation and I say, okay, well this right here kind of looks like cos negative theta, right? So if I am comparing these two, right, so if I'm considering this negative theta, then that means theta is really just 5 pi over 8. Right, so if I'm making it look like this. So that means, okay, right, so if this is cos negative theta, then that means according to the formula, right, so I'm going to put star here, so I'm applying star here. So if that's cos negative theta, that means it's equal to cos positive theta according to our formula. And if theta here is 5 pi over 8, that means my equivalent expression is cos of positive 5 pi over 8. All right, the next one. This one's going to be a little trickier. So it says tan of 3 pi over 8. So this one isn't kind of easier like this one was. If you notice here, we had one side equal to the other, right? So we had negative theta, negative theta. Here, we've got tan and then a positive theta value. So it's not going to work for the right side because our tan doesn't have a negative in front of it. So that means we have to work with this left side here. Okay, so can I manipulate this? So I obviously know that theta is not 3 pi over 8. Right? Because if it was 3 pi over 8, it would be tan negative 3 pi over 8. So, okay, I want you to think of it like this. I want you to manipulate it so that it looks like tan negative of an angle. So notice I'm doing this. So I'm rewriting this as tan negative of, so -1 here, and then negative 3 pi over 8. So I'm making it look like here. So I want it to look like negative something. As is, it just looked like positive. But we know we can change any positive number to a negative by just putting by making two negatives there. So have I changed the expression at all? No. Because if I were to ask you to simplify this, you would say two negatives make a positive, and then I'm back with the same thing I started with. So I manipulated it to look like something that would make it easier for me to compare to the expression up here. Okay, so up here in purple. I'm going to star here. Purple star. Okay, so if I write it as negative 3 pi over 8, then that means if I were to compare it to this side of the equation, that means theta is actually negative 3 pi over 8, right? Because that means it's this part here. So if tan negative theta, which I've written here, is equal to negative tan theta, okay, so I'm going to apply that in the next line. That means I know, so what I just said, so tan negative theta is equal to negative tan theta. And remember, theta is negative 3 pi over 8. So my new expression is, my equivalent expression, sorry, is negative 1 times tan negative 3 pi over 8. So we knew that this equaled this, but all we had to do is figure out what is theta, and theta has to be the little guy in the brackets here. And then all you're doing is plugging it into the right side. Okay, so I know that looks kind of ugly, but it is an equivalent expression, and you can always double check by typing that into your calculator and making sure that you get the same thing as when you type in tan at positive 3 pi over 8. All right, the next one here all has to do with just working with this one right triangle. So part 3 is using complementary angles. So complementary angles refer to angles that add up to 90 degrees. So working with this right triangle, I want you to label this one here. We know that's 90. So we're going to label that in our radians. So that is pi over 2. Okay. All right, now I want you to label one of the other angles theta. So I'm just going to label it A up here. Okay. All right. According to what we know about triangles, we know that these three angles add up to 180. Because I know that this angle here is already 90, that means I know that theta plus this angle have to add up to 90 as well. All right, so these two have to add to 90, so that's 90, and then they complete 180. So how can I write this angle in terms of these two angles? So I can write angle C as 90, I'll say it in degrees first, 90 degrees minus theta, right? So I'm going to find this. So for example, if I found this as pi over 3, a quick way for me to find C would be doing pi over 2 minus pi over 3. So this guy here, I can write as pi over 2 minus theta. 90 minus whatever that acute angle is. So the whole point of this exercise here is to figure out, you're always going to start with kind of starting from theta. So I want to see how I can write a ratio for sine theta in terms of a ratio according to this angle. Okay. So it's finding what trig ratio of this is equal to what trig ratio of this, essentially. So let's start with the different colors, if that helps. So I'm going to work with theta here, will be my purple. So sine, according to this, is going to be, right, this is going to be my opposite. This is going to be my hypotenuse. And this is going to be my adjacent. So I know that sine theta is opposite over hypotenuse. Okay, so here over here. So according to the side lengths, that's side BC. Oh, sorry, opposite over hypotenuse. I think I did that over there. So that's going to be side BC over side AC. Okay, so opposite over hypotenuse. Okay, so now I want you to ask yourselves, according to this blue angle now, so now I'm going to switch to blue. This is my new reference angle. So according to blue here, now this side is opposite. Now this side is adjacent. And this guy is hypotenuse, right? Hypotenuse doesn't change. So ask yourself now, according to the angle pi over 2 minus theta, what ratio do I have to take of that in order to get BC over AC? So in order to get BC over AC according to blue, I'd have to do BC over AC. So in blue, that's adjacent over hypotenuse. Okay. So if that's adjacent over hypotenuse, that means if that's what ratio? That's cos. So we just found out that sine theta, okay, when theta is obviously an acute angle here, is going to be equal to cos pi over 2 minus theta. Okay, so that's one equivalent expression. All right, let's try working with cos. So if I do cos of theta, that would be adjacent over hypotenuse. Okay. So that's going to be side AB over side AC. So now I want you to switch to a different reference angle here, the other acute angle, and I want you to ask yourself what ratio of angle C would give you AB over AC. AB over AC. So according to blue, that would be opposite over hypotenuse. And that refers to sine. So cos theta is equal to sine of pi over 2 minus theta. Okay? So basically that's saying cos of an acute angle is equal to sine of its complementary angle. All right, lastly, tan. So tan theta, so I'm going to start here, tan theta will be opposite, okay, we're looking at purple, opposite over adjacent. So that is going to be BC over AB. So now we're going to change reference angles to down here to C, okay. According to this angle, what ratio will I get BC adjacent over AB opposite? So adjacent over opposite. So you should be thinking, well, it's not any of the original primary trig ratios, but it is a reciprocal. So if you're doing adjacent over opposite, that means that you're actually doing cotangent, right? So that's the reciprocal or the flipped version of tan. So that means tan theta is equal to cotangent of pi over 2 minus theta. So tan is the only one that has, so these two are easy. You can know sine goes to cos, cos goes to sine. Here tan, you have to think it goes to its reciprocal function of its complementary angle. Okay. Just keep in mind that often these expressions are called the cofunction identities. Okay. So I could say find it according to complementary angles, or I can say find it using cofunction identities, just be able to recognize both. So it says use the cofunction identities to write equivalent expressions for the following. Okay. So here it says tan pi over 8. So obviously in this case here, remember theta in these cases is an acute angle. So theta equals pi over 8. All right, so that means my equivalent ratio, my equivalent expression I'm going to work with, if I have to use cofunction identities, is here in blue. So I know tan theta equals cotangent pi over 2 minus theta. And wherever I see theta, I'm now just plugging in pi over 8. So I'm saying tan pi over 8 is equal to cotangent of pi over 2 minus pi over 8. I have to simplify here by finding a lowest common denominator. So I'm going to multiply top and bottom by 4. So that the LCD is 8. That's going to give me cotangent of 4 pi minus pi over 8, which gives me a final answer of cotangent 3 pi over 8. So I just found an equivalent expression. So this graph would be the same as this graph. Again, enter it into your calculator, and you should get the same value. All right, the next one, cos 2 pi over 5. Okay, So in this case, theta is 2 pi over 5. Okay, and we have to use the cofunction identities. So to make our lives easier, let's work with the green here. So cos theta equals sine pi over 2 minus theta. Again, wherever you see theta, you're going to plug in 2 pi over 5. Okay, so cos 2 pi over 5 equals sine pi over 2 minus 2 pi over 5. So here we're going to have to find a lowest common denominator for 2 and 5 is going to be 10. So multiply top and bottom here by 5, top and bottom here by 2. So we're going to get sine of 5 pi minus 4 pi over 10, which leaves us with sine of 1 pi over 10. So cos 2 pi over 5 is equal to sine pi over 10. All right, the second last one, part 4, is using a horizontal translation. Okay, so we have seen that graphs of sinusoidal functions, sine and cos, are very similar, but they are only horizontally translated from one another. So we basically dealt with that a lot last unit. Okay, so that means that you can find a cos cycle within a sine cycle. Okay, so you can find a cos function within a sine function, but it won't have the same starting point, right? So for example here, this is the graph of sine. Okay, so here in blue, this is sine. So now I want to highlight where you see the nearest cos function. Okay, so let's highlight here. Let's do blue. So the nearest cos function here that I can see, and keep in mind we want to pick functions that still have positive a values. So I want you to find the nearest cos function in this sine graph that has a positive a value. So for example, I'm not going to start down here because that would be a reflected cos. I'm not going to start over here because that's really far away. The closest one here for cos would be here. Okay. That is the nearest non-reflected cos function. So what is the d value there, right? We need to know when does the cycle start, because that's going to be the d value. So right here, that's halfway in between pi, so that's pi over 2. So that means the d value for cos is pi over 2, but everything else stays the same. So if this graph was just sine theta, then that means its equivalent expression is cos theta minus pi over 2. Right? So this is just using translations. Okay, so all you basically did here was you did cos and then only a horizontal translation. Right? Theta minus d. Okay. All right, so let's have the same idea now. So that was when we first looked at a sine cycle. Okay. Now we're going to look at a cos function. Okay. So this is the cos function here. We can see that because it starts at its max at 0. And now I want you to try to find a sine function within cos. Keep in mind, I want you to do the same idea. I want you to find the nearest sine cycle where sine is not reflected. Okay. So the nearest sine cycle where sine is not reflected would be here. Right? And by nearest, I mean closest to the origin. Okay. So there's a cycle of sine that appears in the cos graph. So what is the d value here? Well, I can see it starts here at negative pi over 2. So that means the d value is negative pi over 2. So we are going to plug that into, if no other characteristics changed, we're going to plug that into sine of theta minus d, right? The generic formula for translation. So that means cos theta is going to be equal to sine theta plus pi over 2. And the plus comes from the fact that the original expression always has negative, and if you plug in a negative, you get a positive. All right, so it says find an equivalent expression of cos 13 pi over 12. All right, so if we have to use horizontal translations, that means we're going to have to work with this formula here to make our lives easier. So we're comparing this to this side of the equation. So that means theta is 13 pi over 12. Okay, so that means I know that this expression is going to be equal to sine theta plus pi over 2. So now I'm going to plug in theta. So this is going to be sine of 13 pi over 12 plus pi over 2. Again, we want to find a common denominator, so multiply top and bottom by 6. Okay, that is going to give me sine of 13 pi plus 6 pi over 12, which leaves me with sine of 19 pi over 12. All right, so there we go. We found an equivalent expression of cos 13 pi over 12 is equal to sine 19 pi over 12. And that was using horizontal translations. Okay, our final one, part 5. Okay, we're almost there. This is equivalent expressions based on the coordinate plane. Okay, so what's going to happen here is we're going to compare principal angles drawn in standard position with their related acute angle. So what's going to be a little strange here, highlight this as much as you can. In these formulas that we're going to work with in this example, when they are talking about the related acute angle, they actually refer to that as theta. Okay, so in this example, theta is going to represent an acute angle in quadrant 1. Okay, and then we're going to write every other, we're going to write the principal angle in terms of theta. Okay, so I know that it's a little bit confusing, but just keep that in mind here and you're going to see as we go through. So for example, let's start with if there was an angle whose terminal arm, so we're looking at the red angle, whose terminal arm landed in quadrant 2. Okay, so we're going to deal with this principal angle in quadrant 2. Notice that this angle is always going to be compared to its related acute angle theta. Remember, we're calling it theta in quadrant 1. Okay, so I'm drawing theta here. Because it's its related acute angle, that means this little part inside here, right, between the terminal arm and the nearest x-axis is also theta. So for this exercise, we're planning to write this angle in terms of its related acute. So we know if we were to come up with an expression for this red angle that it would be pi minus theta. So that's the expression for the red angle. All right, so here what we're doing is we're saying sine of this angle in quadrant 2, so pi minus theta, how is it equivalent to its ratio in the first quadrant? So everything is about comparing it back to the first quadrant angle. Okay. So for example, I'm going to say to myself, I know that both these ratios, both their absolute values, right, if I found sine of this and then sine of this, both of them would be positive, right? And that's why I drew cast rule in here, right? A and S, all in sine. So both would be positive here. And they would both have the same value because they have the same related acute angle. So essentially, sine of this angle is going to give me the exact same answer as sine of this angle. So sine pi minus theta is equal to sine theta. All right, the minute, though, that we change the ratio. So what if I did cos of this angle? So cos of the red angle. If I did cos of this angle here, it would produce a negative answer because only sine's positive here. So this would be negative, okay, the result. However, if I do cos of this angle, cos here is going to be positive. So how do I make an expression of this equal to an expression of this? So if I do cos pi minus theta here, if this is negative, that means I have to multiply this ratio by a -1. Right? So cos theta on its own, okay, so cos theta, okay, on its own is positive. Okay. This whole expression here is negative based on Cast rule. So I can't have, I know their absolute values will be the same, but I can't have this side being negative and that side being positive with an equal sign in between, because that's not true. So that's why we multiply this ratio by -1, so that a negative times a positive will equal a negative. Okay? So that's why we put this negative in here. So that negative times positive equals negative. Okay. Same idea with tan. So if I take tan of this angle, I know that tan of theta pi minus theta, I know that this expression is negative based on Cast rule. If I have to compare it to tan of its related acute angle, that's going to be positive again. So that means I'm going to have to take tan of theta and multiply it by -1. And when I do that, that will make the two equal to each other. Okay. So that means this is going to be this is going to be equal to negative tan theta. Okay. So again, same idea. This one's going to be positive. In order to make left side equal right side, I have to multiply by a negative. And we don't want to change the value either, so that's why you just multiply by -1. All right, I want you to think of the same strategies for the next two. So let's draw in quadrant 3, terminal arm in quadrant 3. Okay, so that would be this red angle here. Again, we're always comparing it to theta, the related acute angle in quadrant 1. So if that's theta, so this principal angle would come out here, that would be little theta 2. So we would represent this principal angle as pi plus theta. Okay. All right, so if I find sine of this angle, sine is going to be negative here. So that means if I relate it to here where it's positive, that means I'm going to have to take sine of this ratio and multiply it by -1. Okay. All right, so a negative value is equal to a negative times a positive, so that would be a negative value. Cos is also negative here, but positive up here. So in order to make the two sides equivalent, I'm saying cos of this principal angle is equal to -1 times cos of the related acute. Tan is the only expression that is positive here. So if I do tan of pi plus theta, it will give me the exact same answer as tan of theta because they'll both be the same value and they will both be positive. So that means we don't have to change much there. We're going to do tan pi plus theta equals tan theta. All right, let's draw our angle now in quadrant, where it lands in quadrant 4. Okay. So here it is in red. Again, we compare it to theta in quadrant 1. If that's our related acute, then this little angle in here is theta. So we would represent this red angle as 2 pi minus theta. So if it lands in quadrant 4, that means we have sine of 2 pi minus theta. So according to the Cast rule, C-A-S-T, okay. So according to the Cast rule, sine will be negative here. So this value here will be a negative number. So that means if it's positive up here, we have to multiply this expression by a -1 to make them equal. Cos of this angle will be positive based on Cast rule, and it's positive here. So cos of this angle is going to equal cos of this angle. No changes needed. Tan will be negative here, so when we do tan of 2 pi minus theta, that will be negative result. So when I do tan of theta, it will be positive, so I have to do tan theta multiplied by -1. And that would make those two equivalent. All right, so for these examples here, note that it's specific. It says find equivalent expressions using the related acute angle. Okay, so that means if you can't see that related acute angle, you have to determine it first. Okay, and it's also important to look at what your principal angle is and figure out what quadrant it's in. Okay, so right here we have an angle of 11 pi over 6. Okay, so the first thing you have to do is sketch that out and see what quadrant it lands in, because you need to know what section you're working with here. Okay, so that is 11 sets of pi over 6, so 11 sets of 30. So when you count that out, okay, it should land in quadrant 4. Okay, so in this case here, and it's also easy to see the related acute angle. It's always, if you read to yourself that this is 11 sets of pi over 6, then in this case here, we're going to say beta is pi over 6. Okay, and remember that's important here because in these formulas, theta is beta. Okay, so just getting used to that here. So theta in this case is pi over 6. So you need to rewrite cos 11 pi over 6 in one of these, in this form here, right? So we need to write cos of 11 pi over 6 as 2 pi minus an acute angle. So we found the acute angle, and we know it's in quadrant 4. So that's why I can rewrite this expression as cos 2 pi minus pi over 6. Okay. So notice I put a little blue star here. Okay, so blue star here referring to this formula. Okay. So we just rewrote this as its angle in quadrant 4. We found our beta. So now that we have this side, I know that cos 2 pi minus pi over 6 is equal to cos of the related acute angle. So I know that that's equal to cos of theta. Okay. And that's where you can plug it in here. Okay. So that means cos of 11 pi over 6 is equal to cos of just pi over 6. And that makes sense because cos here would be equivalent to cos of its related acute angle up here based on Castro. All right, part B, we've got tan 5 pi over 4. So right from here, I know this is going to be 5 sets of pi over 4. So I already know that my related acute angle is going to be pi over 4. So theta will be pi over 4 in these formulas. So that's 5 sets of 45 degrees. So that's going to land in quadrant 3. Okay. So this is the angle we're working with in green, 5 pi over 4. And then the related acute angle is pi over 4 in here. So remember, you always have to rewrite this according to whatever quadrant it lands in. So we're going to rewrite tan 5 pi over 4 as pi plus the related acute. So that's going to be pi plus pi over 4. I put double star here to show you I'm referring to the double star formula here. So we know tan of pi plus theta is equal to tan of theta. So this is just going to be equal to tan theta. Okay, and I'll do that little arrow again. Okay, the related acute angle in this case is pi over 4. So an equivalent expression of tan 5 pi over 4 is tan pi over 4. Okay, and that is it for all the formulas. Like I said, usually on the formula sheet that you're allowed to use on tests and things, these ones are not on it, but everything else is for final assessments. All right, so just to summarize and make sure you can kind of recognize some things here, it says prove whether the following expressions are true or false and justify. So it says, are these two expressions equivalent? So left side is cos theta, and right side is negative cos theta plus 4 pi. So I immediately notice that this section here looks like the period function, right? So you know how we normally had theta plus 2 pi and then times n, like times some one integer? So this looks like negative cos theta plus 2 pi n, where n is 2, right? So if I put 2 in there, that'd be 4 pi. So is that true? If we go back to our first page, is cos theta equal to negative cos theta plus 2 pi n? Okay. That is not true. Okay, so if we go back to our first page, cos theta is equal to positive cos theta plus 2 pi n. So left side does not equal right side as, oops, there, since of that expression, so therefore it is false, that statement. Okay, so we can go up here and kind of cross through the x. Okay. All right, we've got tan pi minus theta equals tan theta. All right, so this one here, just noticing the pi minus theta, that looks very familiar to the expressions we just did, right? That looks like this one here, tan pi minus theta. Okay, so it says tan pi minus theta is equal to negative tan theta. Okay, so we have left side equals that, but we have right side equals positive tan theta. So left side does not equal right side because we just looked back and tan pi minus theta should equal negative tan theta. So therefore, this statement was also false. Okay. So left side does not equal right side there. All right, and here's just a summary of all the equivalent trig functions. Like I said, these are the ones that you will get always on a formula sheet. But keep in mind, like you never, I don't want you to think you have to memorize them, but I don't want you so much to memorize any of the others. I want you to understand where they come from. If you understand the relationship, you never have to memorize anything. Okay? All right, so I hope you enjoyed this. I know it's a lot of information to take in, but at least you know you always have that formula sheet with you. Just please make sure you understand when you are using the formulas, if you understand what they actually mean. Okay, please let me know if you have any questions. Just a few homework questions here. Do as many as you can, and then let me know about any questions you have. All right, good luck.